I told you that last thing I would like to mention here is the deterministic policy gradient. And the deterministic policy gradient is when you have your policy network only behaving deterministic. This means that you just give it this state. You would say, I'm in this particular state, and then it's going to give you back the optimal action that you can do. It's like you have an optimal a deterministic policy, right? Now, you might tell me that why you are doing this, because if we are doing a stochastic process, stochastic policy, this means that I have a general pi, general distribution, and then with the stochastic policy, I am also including the deterministic policy as well, right? So stochastic policy is more general form of policy as compared to deterministic one. That is correct, but sometimes it is going to be more efficient if you just directly work with the deterministic policy, especially when you have a continuous action space. So I think I told you this in the very last part, last description, last session. So when you have one arm, for example, and you can move any place in this space, then when you use those stochastic approaches, like there are tricks to just kill that randomness, but you're going to see that this guy is going to get a bit shaky around the target, right? Whereas if you have a deterministic policy, it's not going to sample anything, right? So it's just deterministically going towards the point. So which direction I want to go when I am here, so it's going to be a specific direction, right? So there's no randomness anymore there. So it could help a bit in that sense. Also, as we're going to see, it's going to help you in sense of sample efficiency, because effectively you can do what you did in deep Q learning. So you can do off-policy learning. This helps you with sample efficiency. So there are some benefits in that, and we're going to talk about this. You're going to see that this is basically deep Q learning again, but you have one extra network which is just telling you what is the optimal action. So yeah, when we have continuous action space, or policy is basically a density function. When we have discrete action, we have a policy which is basically a probability distribution. So this is a policy, right? A policy network. The policy network has a bunch of parameters. It's going to look at your state, right? If you are thinking about a discrete case, right? You can only go 4 directions, left, right, up, down, right? Then in this case, your policy is going to give you a probability distribution, maybe a softmax output. And then as the input to your network, you're going to give one, representation of your state, the image of your current state, right? You're going to give it to your network. It's going to give you a bunch of probabilities. Now, if you want to act, you're going to sample that distribution, right? This means that if you are exactly in the same state, and say the 4 chances are like half, 0, 0, then 50% of the time you do action 1, 50% of the time you do action 2, 0% of time you do the rest of actions, right? So that's going to be the case with deterministic, with a stochastic policy and discrete actions. When you have a continuous action, so you typically just describe your policy by the statistical parameters of your density function using this state, right? So this was the example I gave you initially. So this is a kind of nice example that you can consider to visualize what is happening. So you look at the representation of your state, this XS, is going inside a deep neural network, right? And then at the output, you are getting something. You treat it as the average of your action, right? You would say my action is, for example, normally distributed around this mean with some variance, right? Maybe you have your network more sophisticated and you compute the variance as well. Maybe you consider another distribution, right? But this is, again, a typical thing. So you're going to start from one state feature, and then you do some processing. You end up with a kind of known distribution, and you sample from that distribution, right? So every time that you want to do an action, you are going to randomly sample one action around that average action with that variance. This is the way that you are going to sample. Now, how we can do deterministic policy? So we can actually do deterministic policy by thinking about a distribution which is indicator distribution, right? So you give this XS, the representation of your state, to your policy network. It's going to give you one action. Do this action, right? The probability of that happening is 1. The probability of anyone else happening is simply 0, right? Now, what are the reasons that we are going for that? Well, there are a bunch of reasons for that. One of them is because when you are dealing directly with the action instead of its probability, then you can somehow kill the actions which are dangerous, right? So there's some sensitive applications where you cannot do any action, right? If you want to inject something in the for a patient, right? You cannot simply do any action, and you would say, "Oops, sorry, that happened." It cannot happen. Right? This is life. Or autonomous driving, right? You cannot simply randomly sample the action, even if the probability of just turning left is very, very small, right? 10 to the power minus 8, right? But what if that sample happens, right? Then you're going to just hit the other car, and it's life again, right? So sometimes it's quite dangerous, but if you are dealing directly with the actions, then you can kill that output at the policy network. And yeah, there are a bunch of other reasons in practice that happens, but as I said, mostly this is because when you are dealing with a continuous action, sometimes it's easier to directly focus on the action itself. Now, sometimes you do not have enough samples. So when you have a continuous action, then this means that the space of action theoretically is infinite, right? And then if you want to have a feeling about the distribution that you are learning, then essentially you need infinite samples. You do not have it in practice, and then this is going to sometimes make challenge. So probably you don't want to, if, again, the distribution is not that well intuitive for you in the particular application, like, for example, moving your hand, you don't really know whether you need to just make it Gaussian or not, right? The only reason you make it is simply because you can sample Gaussian distribution by your computer, right? So this is the reason. And well, you don't know whether this is the best idea or not. Maybe we can focus again on a deterministic distribution. There are a bunch of reasons like this. But as I said, continuous actions is the most important thing. When you have a continuous action and you want to be sample efficient, then going for a discrete policy gradient is a kind of good move, a good choice. And you're going to see why. Okay. Now, what is a discrete policy? This is the discrete policy, right? Your policy is basically telling you, given this state, what action you should do, right? And that action is the optimal action. Supposedly, this is the guy which is maximizing your action value, right? This is what you want, right? And now, what you could say, this parameter theta, your neural network is basically computing or choosing the optimal action only, right? So that's what your network is. So the deterministic policy network looks like this. Every state that you're in, you're going to give your feature representation of this state into your network, and then at the output of the network, you're going to have the optimal action, right? So you are in this location, then the right direction to go is this, right? And then you change the state, you're in this location, then the right direction is this, and so on, right? So every single state, every single location in the space, you're going to have one specific optimal action, right? So this is the deterministic policy network. This is, again, a policy network with this difference that your policy is basically just an indicator function. So you throw away the policy itself, and you only look at the optimal action, right, which is going to happen with probability 1, right? Now that we have this guy, now the question that you might ask is that how I can train this. Now, one basic answer, or say a classic answer, is that, okay, let's treat deterministic policy network as a policy network with indicator distribution, right? So the density function is simply the impulse, right? It's going to happen with density infinite or probability 1 exactly for the action that we have chosen as the optimal action. Any other action is happening with probability 0. Density is simply 0. You can do that, but it turns out that you can do it more efficiently. You don't really need to get through all of the policy gradient theorem anymore, okay? Because, yeah, somehow if you just ignore the fact that a neural network is doing this for you, then you basically get back to the Q-learning problem. And we're going to see this. So we don't really need to establish a new approach. As I said, one can just take time, write down everything for PGM using the indicator function. If you do the math right, then you're going to end up probably with the same thing we get here. But we can just do the simple way, and that is that we focus on deep Q learning, right? So we're going to think from deep Q learning point of view. We again do DQL, but this time with this fact that we have this genie, which is going to be the neural network, who is going to look at this state and gives us the optimal action. Okay. Now, yeah, let's just get back a bit on the optimal policy notation. So what we discussed at the very end of chapter 4 was that if we want to do Q learning and we want to do it using in a space in an environment with continuous action space, the problem was that you give this state to your neural network, but at the output you need to find out what is the optimal action, right? What is the action with maximum Q value, right? And you could not do it because your action in space is continuous, right? You effectively have infinite number of, theoretically have infinite number of actions, right? So that output is very, very large. You cannot really just do this by a neural network. You can quantize it. This is not probably working fine. And the other thing is that you can also not simply think about optimizing the output of a general function, which is represented by neural network, because then that one is, again, the same complex problem, right? So the way that we came up with a sort of idea, which somehow ended up by somehow assuming that a policy network could potentially help, and this motivated us to start chapter 5, was that we said, okay, what if we have this network, this kind of, genie, who is looking at this state and is telling us what is the optimal action, right? So it's going to look at this state. It tells us, okay, if you do that action, this is optimal. Why? Because I know, right? And now, if you do know that this is the optimal action, then you can still do Q learning, right? Because you would say, okay, I don't really need to look at the general state representation. I just look at the representation of a state and optimal action, right? And I do know what is the optimal action, right? So that guy, the optimal action and this state go inside this network. I am going to train this guy to learn the Q value for this state and action given the policy, right? And then given that this action is coming with the optimal policy, is optimal action every time, then essentially what I am evaluating here is the optimal action value, right? So at the end of the day, in Q value, Q learning, what do I want? I want to get the Q function and take the maximum over actions, right? But I already know which guy maximizes it, right? So I don't care about the rest, the remaining actions, right? I take this guy and directly I inject it inside the Q learning update, right? And I keep on going Q learning. And every time, instead of maximizing over action, I simply get the output of this network, right? So if I have this guy is going to help me in the sense that I can still do Q learning even though my action space is continuous. And this guy is now the deterministic policy network, right? If I have a deterministic policy network, supposedly that guy is giving me the optimal action. This means that I am able to play with the optimal action in every single state, so I can basically do Q learning. You got the idea? Yes? I'm going to open it up now, but everybody's clear, right? What this policy network is doing here, right? So, yep, that's again, yeah, Q learning. But if you want to talk in general, well, this is again a kind of actor-critic approach, right? Because this is a kind of actor. This is the policy network acting, and then you have this critic, which is a value network. But you can also look at it from the DQL point of view with a kind of genie actor, right? Who knows what is the optimal action. Okay, now, so yeah, the optimal action value at every single state is actually the one which is coming out of this network, and that is the one which is maximizing the Q value over all actions, because our network, or policy network, or deterministic policy network is actually finding us this particular action which does the maximization. Okay, now that is going to be the key idea. So what we could say then, we would say, okay, when we are doing Q-learning, what we want to do, we want to just tune our parameter theta in a way that for every single state, is actually or it's somehow estimating the optimal, the value of the optimal policy, right? And given that we do know this parameter, this action here, given by our deterministic policy network, is the optimal action, then when we put it here, we simply need to just optimize everything with respect to maximize this guy, right? Why? Because the optimal policy is having the maximum Q value, right? So if you play with the optimal policy every time, if in every single stage you play with the optimal action, then the Q value that you get is maximized, right? So it makes sense that you try to find your parameter of your policy network or deterministic policy network in a way that somehow maximizes this guy, right? So you have your Q value, which is coming from the Q network, right? And then you compute it exactly at this state and action pair that is given by your policy network. And now how can I train that policy network? Basically, I make it maximize this value, right? Now, if I want to do that, what should I do? I need to take the gradient of this guy, right? With respect to what? Pay attention here. With respect to? I'm doing it with respect to theta. What is theta? Parameters of? Yes, the policy network, exactly, the deterministic policy network. So W is the parameter of your Q network, right? And right now I am not touching that one. I'm going to update that one as well, right? But right now, say that, for example, at this point, say that Q network is trained well, right? If the Q network is trained well, it is able to look at the state and the action and gives me the Q value, right? So now I just want to find out how I should tune or how I should update my policy network. I would say, okay, the action coming out of the policy network should maximize this Q value as well, right? So here W is fixed. I'm going to take the gradient of this guy with respect to the parameters of the policy network, right? And how does it work? How can I do that? I can write chain rule, right? I can take the derivative of this guy with respect to the second argument, the action, right? And then multiply it with the derivative of the action with respect to the parameters of the policy network, right? So I can write it down in this form. Everybody's cool about that? So this is the Q value that you get, right? QW. This is the Q value that you get for state and any action. Now I take the derivative with respect to action, right? Times the derivative of the action with respect to the parameters of the policy network, right? That's just a simple chain rule. Everybody agrees? Now, this guy, I think this is quite clear for you, right? This is backpropagation over your policy network, right? State goes in. You get at the output the optimal action, right? You can backpropagate all over the network. You get all the gradients, right? Cool. What about the first term? That is again backpropagation, right? But over the value network, the Q network. Why? Because the state and optimal action both together, right, go inside your Q network, They compute everything till they get to Q value, right? Now, if I want to know the gradient of or the derivative of this Q value with respect to the action, what should I do? So from this guy, I backpropagate all the way to the input, right? Correct? So this is the same thing you do with encoding, decoding in deep learning, right? You have your encoder, gets data, it processes it, encodes it, right? Then you get the encoded version, you decode it, you get what you want, right? Now when you want to train, what you do? You backpropagate over all of it, right? You start from the very output, you backpropagate, you get to the input of the decoder, but that guy was also computed by the encoder, right? So you keep on going backward, right? You backpropagate till you get to the data, right? And then you would say, okay, I have all the gradients I want, I can update. Same thing is happening here, right? So you're backpropagating over your policy network, and you're also backpropagating once over your Q network, right? And in practice, when you want to update every single iteration, you would do that, right? Anyways, because even if you don't want to directly apply it here, probably you want to update your Q network, so you need to backpropagate over that, right? And you know that when you do backpropagation once for one sample over the whole network, you're able to compute any derivative that you want, right? So this derivative is somehow hidden inside that single backpropagation you do on the Q network, right? So moral of the story here is that if you want to have an estimator of the optimal action value function, what you can do, you can simply backpropagate once over your policy network, once again over your Q network, and now you have everything that you need to update both networks, right? Because for update of the Q network, you need backpropagation over Q. For update of the policy network here, you need backpropagation over Q and policy, right? So both of them, you just backpropagate over both of them, which makes sense, right? If you are doing any neural network, every time you want to update, you should backpropagate. But it's just one backpropagation, nothing more, so everything's cool, right? Everybody got the idea? I'm going to explain more. Yes? Right, right, definitely, yes. You're right, right. It's because it's again actor critic. That's correct, right? Okay. Yeah. Yeah, I'm thinking of it like that. Yeah. That makes sense. That makes sense. Totally makes sense, right? Okay. So now, yeah. What is it here? So yeah. Okay. Eyes don't help here. So yeah. What is that? Bellman equation, but why? Oh, why I need the Bellman equation? Okay, okay, yeah, okay. So, yeah, one thing that I now want to see how I can collect samples when I want, yes? Here? Right? Here? Oh, here you mean? Output of this guy goes inside the Q network, right? No, it's not giving you the optimal action. You want it to give you the optimal action, right? But then the question is that how you can train it to give you the optimal action, right? Yeah. Sorry? Policy network, yes. You want to make it, you want to train it in a way, so you want to find theta in a way that it gives you the optimal action, right? And then the question is how you know how you can make an objective for having an optimal action. And then we do it this way. We say, like, if that guy is really optimal action, this whole Q value should be maximum, right? Among all the actions is the one which gives me the maximum value, right? Q value. So I need to just maximize this guy. This is the objective, right? For the policy network. Because mu itself is giving you a deterministic action, right? So you go over multiple training data, of course. and then you're going to see different trajectories. You train this guy. But when this guy got trained, finished, then any state that you give to it, it's going to give you one action. It's not going to change the action. Yes. Yes. Every action that you do is somehow the one which is deterministically used by your agent, and then Q network is only able to evaluate that guy. But assuming that that action is the optimal action, then the Q network is estimating the optimal Q value, right? Make sense? Questions? Okay, so now, yeah, sorry for the confusion here. Now, I want to just find out the way to just sample, collect some samples by which I can actually estimate the Q values when I want to update my Q network in Q learning. Now, how can I do that? Well, I would say my Q network is supposedly estimating this optimal Q value function, right? Q function. And then the optimal Q function in one given state and action is going to be the immediate reward plus this term. This is what we have inside the Bellman equation, right? But now, inside the Bellman equation, this is the optimal equation for Bellman, which says that you're not supposed to just average the next value, but you're going to take the maximum among all Q values. Remember that, right? So if you are, just as a recall, if you are just talking about one particular policy, then the Q value of the policy, it means that instead of a star, you have pi. For given a state in action, is going to be immediate reward plus expected value, right? V, correct? That was the case when you have a classic evaluation by Bellman equation, right? But when you think about the optimal policy, this is why I put a star here, then the optimal Q value at one given state in action is going to be immediate reward plus. The next thing that you have is the expectation of the value of optimal policy, right? And that value of the optimal policy is the maximum value among all action values, right? Maximize over actions, right? This means that you can replace that V with this guy, right? So this was the optimal equation for Bellman optimality equation. And now, if I want to use my network to somehow sample from this equation, the thing that I can do, I can simply directly replace the output of my deterministic policy network, right? So this means that if one state goes inside the deterministic policy network, you're going to get one action at the output. That is supposedly the optimal action, right? And then if you give it to your Q network, which is estimating the optimal Q value, right? If you give it to your Q network with the next stage, right? The next state that you see, then these together are going to give you basically this value, right? The maximum Q value among all possible actions in the next stage, right? So you have this guy, you have your immediate reward, you have something to take as a sample for training your Q network. Okay? Did you get the idea? If no, no problem. We're going to do it right now. Okay. So say I have one particular time step. So I'm time step ST. And, yeah, okay. This is ST. Mu of ST. Sorry, typo. Again. So here is the policy network, of course, computed at ST. Just fix it. So you're in one particular time step. You have the state, right? Then that state goes inside your deterministic policy, going to give you the action, right? This is the action, the optimal action for that state, right? So you play with that action, correct? Then you're going to get an immediate reward, and you get into the next stage, right? Now, what you could say that, well, this action in the next stage, right? So if I go to the next state, if I want to know what is the optimal action, I simply need to give that state to my policy network again, right? So I'm going to get that ST plus 1. I give it to my policy network. It's going to give me the optimal action, right? Now I have the optimal action for the next state. I do know what is the next state. I'm going to get this term, right? If I add it up with the immediate reward that I collected, this is supposedly the estimator of what I have as the optimal Q value in the current time, right? This is the basic temporal difference. Everybody sees that? So I can take that guy to be my estimator of the Q value, right? Every single time I'm in this state, I look at the next state, I give it to my policy network, it gives me the optimal action. I give these two guys into my Q network, I see some optimal value for the next state, right? I take that guy plus the immediate reward I get, I can build one label, right? And this label should be the label that I see right now by my Q network. I don't see it, I try to minimize the difference, right? And this way I can train my Q network, right? So this was the same thing we did by Q network, by Q learning. But when we were doing Q learning, since we did not have this policy network to give us the optimal action, we had to give it to the Q network. We look at all the values. We take the maximum one, right? But now we don't need it anymore. We get rid of that issue with the continuous actions, right? So I'm going to get this label. So what I want the Q value at the current state and action to be exactly the label that I am estimating, right? Or roughly that one. So I try to just minimize this difference, right? So you sample one trajectory again. Every single time you build a label for your Q and action. And you build it based on using your policy network and Q network, right? And now that you have labels, you try to just look at the outputs at every single time and reduce or minimize the difference between the two, right? This is going to somehow train your Q network, right? Everybody's cool? So, no TRPO, no PPO, no trust region, nothing. Life easy, right? So, if it's really continuous action and if you're not so much obsessed with PPO or trust region, you can simply do that. And this is going to work, definitely. Questions? You got the idea? Great. So this is going to be the way that you're updating your policy, Q network. So this is the loss function that you have. You take the gradient of this guy with respect to weight. Well, we have done it so many times in the previous chapters. Basically, it's going to be 1 delta, which is this difference, times the gradient of the Q network itself. But this gradient is with respect to weights. Again, if you backpropagate over your Q network, you already have this gradient, right? So backpropagation over policy network, backpropagation over Q network, you have whatever you need to update both policy network and Q network, right? And then, yeah, that's going to be your next weight, and you keep on going, sample, update everybody. You keep on going till they converge, right? Great. Now, this is what we call a deterministic policy gradient, DPG. So there are different versions of it. DDPG, deep deterministic policy gradient, is the one, which is this guy, plus a bunch of tricks. And then you have the twin delayed deep deterministic policy gradient, and so on. And all of them use the same idea. Deterministic policy network, a Q network, both together try to train. Then you see some issue in between. You try to resolve it, and you give it a new name, right? That's it. OK, so this is the dummy one, or basic one, vanilla one, that we already developed, right? So how we are doing, how we are training our network, we have two networks. One of them is the Q network. The other one is the policy network, which is mu theta. And we want to update both of them. Well, we start by sampling. So we sample a trajectory. And for every single time step, the thing that we are doing, we are looking at the optimal action in the next time step. Why we can know it? Because we have the policy network. Since we see the next state, we are going to say what is the next optimal action, right? So we have the next optimal action. We get a label, this R plus Q of next time. This is going to be the label for our Q network. and then we compute the difference between this label and what we get out of our Q network at this time, right? So at this time, Q network is giving us Q of ST and AT. And then if you want to get a label or a sample label, you would say, OK, immediate reward. So I keep on going with this one because no. Okay, I keep using this one. Maybe they answer at some point. So yeah. Okay, so yeah, if you want to really do that, so the classical approach is that you're going to use this. You're going to add a bit of noise around it, right? And the variance of that noise that you're adding is going to be proportional to the action that to epsilon, right? So Z here is, for example, a Gaussian noise. Not only no answer, but we got lost. Okay. Anyways, yeah, I can do it like this. So I just want really badly to finish today, so I don't bring you here next week. So if I have one action, if I want to do epsilon greedy improvement, the thing that I can do, I can add up a bit of noise, right? So my action tells me. Okay. Okay, now the action, you are going to add a bit of noise around it. So the noise power is going to be proportional to the epsilon that you want. So if you increase epsilon, this simply means that you are adding more randomness. You are exploring more. If you reduce epsilon, you're just doing the action that the policy network says. So you are doing less exploration. You are doing more exploitation. So you can simply do that. One thing that you might say is that, well, this Z value, this Gaussian variable, this could potentially just take you out of the region that you can work in, right? So for example, say your actions could be anything between 2 and 6. So the value that it can take is something between 2 and 6. And then when you add noise, it just somehow exceeds 6, right? How you can resolve that issue? I guess this is not a big deal, right? You can just simply clip it, right? And this is the typical thing you see in the DDPG implementation. So you get the output of your policy network. You add up a bit of noise. That noise is proportional to the amount of exploration you want to add. And then you're going to clip it with some minimum and maximum action, right? You would say, anyways, I don't want to exceed this input value, and this, I don't want to go below this value. So you simply do that, right? Makes sense. And next thing about replay buffer. So you can do it exactly the same way as we did it in Q-learning. And as I told you, the main reason is that you are just targeting the optimal policy, right? You want to know the optimal Q value. You are just looking into the optimal version of the Q. You don't care what samples you have, right? You are not evaluating the policy that you're playing with, right? And because of that, you can essentially do efficient experience replay. So basically, you keep on playing, and every time that you play, you're going to collect those samples into a buffer. And then every time that you want to train your Q network or policy network, you go over that buffer, you sample from that one a mini batch, and then you train based on that, right? So yeah, that I think this is again the same thing as I just tried to explain. One, you might ask me that, okay, in the PGM you told us that it's not sample efficient because, I think someone, yes.
Hi there, Professor. I just wanted to call and say, unfortunately, because it's past 6, we won't be able to provide batteries.
No worries. Okay. No. I thought it's the battery. Sorry. Okay. So yeah. So in the policy gradient method, you might tell me why we were so much restricted in terms of the sample efficiency there. Well, basically there we were playing with one policy, and then we used our value network to evaluate that policy, right? But the Q network here is not evaluating the policy that we are playing with. Even if we play with a random policy, it still tries to evaluate the optimal action value function, right? So at every single state, you're just doing one action, and that action is you have your policy deterministic network, which is able to give you the optimal action, right? If you even deviate from that action, it doesn't matter, right? At the end of the day, when you want to sample, you have the optimal action of this next time, right? And you can say how you can actually improve your Q network to get into the optimal value. So again, same as Q learning, you're basically working off policy, and this gives you a high degree of freedom in terms of the sample efficiency. So when we were doing Q learning, we said like we do some action, and now that we did action, we get the state and reward from the environment. Then we're going to save everything inside a replay buffer, and every time that we want to train, we are going over this network, right? Over this buffer, sorry. We sample a mini batch from it. Every single pair is going through this network. You're able to get the label. How you can find the label? Well, you could say that the next state, this is the next state inside the sample, goes inside the Q network. I am going to take the one which has the optimal action, maximum Q value, and this is going to build the label for my Q network, right? And then I try to make my Q network at the particular state and action to play like or to get close to that label, right? This is what we did in Q network. Then again, we can do the same thing here. The only difference is that here we had to take the output of the Q network, which is maximum, but now you already have the policy network, right? So the policy network going to take care of that one for you, right? So this is the thing that you are going to do again. You're going to act using your policy network, right? When you act, you are getting something from your environment. Again, you save it in the buffer. Each time that you want to train your network, you're going to sample from that buffer. And then when you want to build your label, again, you're going to look at the next state inside your sample, right? This is the magic happening, right? So next state is SB plus 1. You give it into your policy network, which hopefully got a bit trained up to this point and is able to somehow estimate what is the optimal action. So now this guy is your label, right? Immediate reward plus the next action value, right? And then you're going to take this one, you try to get close to this guy, right? And you don't care about what was the sampling policy, right? That is why you can go off policy. So obviously, you can go with this guy. You can do much more sample efficient training. You can just sample a batch of trajectories, and you can use them over and over to somehow get into some acceptable result. Then you can throw them away, sample new trajectories, and then you repeat this till you get into what you want, right? Now, last thing regarding the target network. So the issue with the target network, I guess you remember, the problem was that when you are computing your labels, so every time that you are computing for the label for the current time step, you are going to use your Q network, right? The next state and the next action, right? Next optimal action. This is going to go inside your Q network. It builds your label, right? But then you get that label and you train your Q network itself, right? So you update W itself. This means that your label is going to change. We talked about this, that this is going to make a bit of trouble because each time that you have your label, you want to get into this point, but when you move, your label is also moving, right? And it somehow makes the convergence problematic. So how you can avoid this issue? Well, we can copy a target network, right? When we are training the Q network, we're going to copy it first into another target network. We use that target network for quite some time to compute the labels. This guy is not changing in parameters, so it's going to give us consistent labels. And then we train the other online network, right? Once we have gone over multiple epochs, multiple iterations of training, then we're going to copy that updated version into our target network. Again, we keep on using that for multiple iterations. And we keep doing this because every time we give the online network a chance to converge to something, right? And then this one gradually is going to go up, right? Same thing you can do here, but here you should also copy your policy network, right? Because you don't want every time you also update your deterministic policy, right? You don't want your action to now move, right? The optimal action. So you need to keep both of them consistent. So the idea here is the same thing. So yeah, this is the target network as we had in the Q-learning. So I have this guy, I copy it here. I keep this guy for computing the label, the lower one, the target network. And every couple of iterations, every H rounds of updates, I'm going to copy this guy again here. So this gives the chance for the upper one, the online network, to get trained. Same thing you can do here, as I told you. The only difference is that each time you copy your Q network, W, and your policy network, theta, both of them, right? You copy both of them into the target networks. Then you can use those guys to compute the target ones to compute your label. You have the label, you train for multiple rounds, right? When it somehow gets into a kind of stable situation, then you just copy it again and you keep on going, right? Everybody's clear, right? Questions? No question? Okay, so if you got no question, then this is going to be DDPG. This is the algorithm that quite widely used for, RL application with continuous actions when you are limited with the number of samples that you have. One of the very well-known applications is application areas is robotics. Like in robotics, you usually need to sample with a real arm or a real robot, and then this is going to make your sample efficiency quite crucial. So you cannot simply simulate the environment perfectly. And in that sense, well, this is a better approach because it's going to be more sample efficient. You can use your samples over and over. Okay? And it's much easier, right? I mean, as compared to PPO and TRPO, it's much easier to make it work, right? It's not that complicated, really. The updates are quite simple. Okay, that's about this. And there are a bunch of other things that could happen with DDPG. One of them is overestimating issue. Like you can use DDPG, but your Q network is going to shoot overestimates about the Q value. Why this is happening? Any idea you have about this? Do you remember we had it also in Q learning, right? We said that Q learning could give bias, right? Overestimate. What was the reason? Do you remember the reason? What is it? Just go ahead. Maximizing. Perfect. Maximizing was the main issue, right? When you do maximization, then it somehow adds some sort of bias, right? Some overestimate when you are. Now, what was the idea how we could get rid of that? Dual Q, yeah, exactly. Dual Q learning, right? So you would get one set of one set of Q networks for sampling, one set of Q networks for evaluation, right? You find the maximum action here, but then when you want to sample the Q value, you use the other one, right? And we said since they are independent, then it's going to reduce the bias, right? So you can do the same thing here as well, right? And if you do that, this is going to be what we call a twin delayed DDPG, right? You could have, as similar to the Q learning, you could have action values estimated with significant difference, significant biases. One thing that you might tell me is that I told you in Q learning that is not a big deal, right? So sometimes you just estimate Q values with a bias, but that does not impact your optimal action. Because, for example, the value for every action is biased roughly with the same value, right? And then the optimal action is going to be chosen, is going to be the same again, right? And we had this particular few examples, and I showed you one of them that even though it had bias, but the optimal policy was not changing, right? But the point here is that in DDPG, it could be more crucial. And the reason is that in DDPG, what you're doing, you're using the Q values to also update your policy network, right? So when you are computing the gradient of the policy network, Q also shows up there, right? If Q is significantly large, then that guy could essentially increase your gradients, right? It could explode your gradients. And this is something that you might see, okay? So it's not because it's going to impact the optimal action. It's basically making the training a bit problematic. And this is important here to get rid of this if you see it. Like, not in every application you're going to see it significantly, but in many applications you might see it. So this is going to be twin delayed DDPG or TD3, and this is the algorithm. This is basically double deep Q learning. It also has some extra sort of tricks. For example, the delay term here is for reduce, like it's a difference between the update frequency of the Q network and the policy network. Like, you keep policy network fixed, I think you keep Q network fixed, you do multiple iterations on the policy network, and then you update once the Q network. Yeah? So this means that your Q network is getting updated less frequent as the other one. Well, this is okay, right? This is going to give you a level of stability again, right? But this is not a very crucial thing. Okay, I think I said it wrongly. Like, policy network is getting less frequently. So when I prepared this slide, I checked it. So now I didn't have it in mind. So I guess this is correct. Okay, so that's about this. And yeah, there are some other tricks. For example, extra noise. If you look at the detailed implementation, for every action you add a bit of noise, and that a bit of noise is going to make your samples a bit independent. And because of that, you can reduce the bias. Well, these are just statistical ideas, and people use different of them, right? Yes?
How many networks are in this implementation?
In this implementation, if you really want to do it like naively, then it's going to be like 8, right? 8. Right, you're correct. So 2 online, 2 target, and then you copy everything the other side, right? But you can actually merge them. So in practice, you can merge them. And it's not an important thing because all the networks, I mean, there are at the end 2 networks, multiple copies, right?
It's just memory.
Right, exactly. It's extra memory, just, right. Questions?